chemistry, which is just an application of atomic and nuclear physics, which is an application of math. Why is this facing you guys? Okay, here we go. So you might just think, oh, you just show nepotism to math because math is your thing. You just think math is the best thing there is because that's what you do, and you want to believe that it's like, it's the top dog. But actually, it's not just me hoping that it's true. It actually is. Math is the top dog, guys. Without math, there would be no science. And without science, there would be no technology. And without technology, there would be no air conditioning and cars and computers and lights. Humanity and society as we know it would not function so optimally. Okay, I know you guys just took a test. But I'm gonna have to give you a quiz because it's Friday, right? If you cannot find one, let me know. I can get you one. There's some. Oh, there's some in the math office. I think there's sharpeners in the math office. If there's not, I can get you a new pencil. We have some spare ones in there. Does anybody have an extra pencil that he can use? Or a pen?
I do.
Okay. Hey, Caleb, come back. Someone is going to let you borrow their writing utensil. Do you do pens? Someone has a pencil. There we go. Thank you. Guess what? Who here has been told you can't use pens for math? Everybody? Yeah.
I haven't achieved that level of confidence yet.
Yeah. No. Got to do math in a pen. That's what mathematicians do. Real mathematicians use pens. And what happens when you make a mistake? You do it all over again. Yeah.
At least you learned it.
You learn it well. Yes, that way. So question number 1 on this quiz. Let me say that R is defined to be (1 over x minus 1). Oh, actually, this needs to be in t, although I could define an R of x. 1 over t squared, 1 over t cubed. Find the limit as x approaches 3, or I mean t approaches 3, of R of t. Number 2. Number 2, parametrize the helix. So I mean, create some R of t. What's that? for any point on this curve C, RT is equal to where that location is at. So what is RT equal to? Question number 3. Question number 3 is given that R of T is that. Find R prime of T. Oh, and Alexis, you may email me your quiz. So take a picture. Awesome. Alexis is really here, guys. She's just watching at home. I can't help it.
Was it chest day?
Huh?
Was it chest day?
It's always chest day. But yeah, sometimes I involuntarily do that because I have tics. You guys know what tics are?
Mhm.
Sometimes people do this. Sometimes, when I was a little kid, I had this tick. I have that tick. Sometimes I just do it. I'm a weirdo. That's nothing new, guys. I may note, guys, that this helix only goes to 1 and 1 and all the way out here, -1. Basically, if you were to project this helix down onto the xy plane, it would make a circle of radius 1. So in your parametrization, you don't have to worry about maybe putting a constant in front of each of the terms. You can just leave it as the number 1. You must think to yourself, how could I parametrize a circle? Its x component and its y component, and then have its t just kind of float off for whatever value it can be. Okay, about 1 more minute to finish up, guys. Okay, please place your final thoughts on that piece of paper and turn it in. Oh, could you put it on the desk, please? Thank you. Okay, so say we have some curve here, we have some point here. Notice that the tangent vector to it, r prime of t, is just like a tangent line, but it's just a vector now. It's a tangent line, but now it's a vector. So what we say is, here's your point, P. This can be some R naught, some initial point, and this can be some R. So it's traveling, and so if this is R naught and R, back in our original formulation, we could also call this R of t instead of R naught, and call this R of t plus some h, where h is an element of the real numbers and h is strictly greater than 0. So it's a non-zero number that we add to the parameter t, so it advances the parameter a little bit. And this point is, say, let's say some point q. Okay. Then we say by vector addition, this vector right here, if you do it in your head, it's this vector right here will be r of t, let's see, minus R of t plus h. Maybe these need to be flipped so that the sign is not wrong. All over h. Yeah, they do need to be flipped so that the sign is not wrong. Because then you just get a negative number or a negative quantity up here. So we'll just make sure we don't get a negative quantity. Even though it doesn't change the numerical value, it changes the sign. It doesn't change the absolute value, change the sign, okay? Then we define, our r prime of t to be the limit as h approaches 0 of this. Which is the derivative. Okay, so if this r of t is now encoding a position, so let's say I have r of t is equal to the position of an electron, E negative. An electron is a fundamental particle found in nature. For all we know, it is fundamental, meaning the electron is not composed of smaller pieces. For all we know, that could be a lie. We always think things like before, they thought that, oh yeah, atoms are the smallest things, they make up everything, and there's nothing smaller than atoms. Then we found out that that was a lie. Then we found out that, oh, atoms they actually have components to them. But these components, the proton, neutron, electron, they're fundamental. We can't break those down anymore. We found out that that was a lie. And then they chopped the protons up into their quarks, and they chopped the neutrons up into the quarks. But then they found that the electron didn't get chopped up, even though it has an antiparticle known as the positron, E+. So that's where we're at right now. We're at the point where we think the electron doesn't get chopped up into any more pieces. But guess what? It probably is a lie. It probably does get chopped up into more pieces. We just don't know how to find that out yet. We don't have the technology to test that in a lab, and we don't have the mathematics for it yet. Maybe one of you individuals might develop the mathematics or the technology to find that out. I'll be right there trying to develop it with you. Okay? But if r of t stands for a position, what would the derivative of a position function represent? The change in position over time is your r prime of t, right? What is the change of position over time? A velocity, like miles per hour or something like that. So we can just call this our v. And shout out to Alexis. I created a new way to denote v, so it doesn't look like an r. Thank you for that. Okay, so then let's go one step further. What is the second derivative of r of t? Yes, that would be, d dt of v, which we can call it a, which is actually the same thing as r double prime of t. It is acceleration. You are 100% correct, Caleb. So guess what? We're talking about some physics now. 10.4 is called motion in space, velocity, and acceleration. Okay. So let's say our electron, E, has a position vector, T. Let's say this electron is in a magnetic field, and its motion is given by cosine of t, sine t, t. Meaning we have the electron moving in spirals. Oh my gosh! Who here has seen videos and pictures of the northern lights? You guys see the aurora borealis? Man, that makes me want to move to Iceland and just live there permanently. The aurora borealis is caused by charged particles hitting the atmosphere from space. And when they do, those really strong charged particles that are emitted from supernovas, from galaxies far away, they smash into the atoms in our atmosphere, and they cause them to go into a coil. Because the Earth has a magnetic field, and charged particles move in a certain way in a magnetic field. So the charged particles enter our atmosphere, and then they start to do this spiral thing, kind of like the helix. Oh yeah, question number 2 was this thing. This is the helix. Question 2 on the quiz. Yeah. So this is very much like a charged particle coming from space and interacting with the magnetic field of the Earth and radiating light. That is what causes the aurora borealis. Why don't we see the aurora borealis here? Well, it's because the Earth has the magnetic field lines converging at the north and the south pole, because magnetic fields look like this. So here's the Earth, and the magnetic fields look like this. You see that? This stuff that I'm drawing here is a magnetic field, typically denoted by B. So it's only at the North Pole where the charged particles can get close enough to be visible, where they're doing that dance, where they're spiraling. So we can see those cool lights because of that. Over here, up in Oklahoma, we don't get that. The magnetic field is way out here. So we don't get to see that cool aurora borealis. But in the northern lights, in the North Pole, South Pole, maybe around Australia, maybe New Zealand, Iceland, definitely Greenland, those places get to see the aurora borealis. It's really cool. So let's say this electron is dancing like this. So this is equal to its position at various times t. What is its velocity? That question is basically, what is its velocity at any given time, t? That question is taking the derivative of this guy. What's the derivative of cosine? What's the derivative of sine? What's the derivative of t? Okay, so at any time, we can say that the velocity of the electron spinning towards Earth, radiating crazy amounts of light, forming beautiful different colors like green, blue, red. Its velocity is encoded by that. Okay, what is its acceleration? It's the second derivative of position, right? So we just differentiate this guy. What's the derivative of sine? So I gotta put that negative on it. What's the derivative of cosine? Negative sine. And what's the derivative of 1? 0. Oh. So it seems like it accelerates in its x and its y, but no longer in the z. Yeah. There's no more z acceleration. So meaning this electron, like thinking about it in terms of physical sense, who knows what terminal velocity is? Who here has been skydiving before? I have not. I have not. I raised my hand just to see if anybody has. But if you ever go skydiving, you notice when you jump out the plane, I haven't done it, but it kind of seems kind of cool, maybe, if you want to die. Or if you want to have fun, it seems like it could be fun. But let's say you jump out of an airplane. At first, it's very scary because you're falling faster and faster and faster. So you get that sinking in your gut feeling like on the roller coasters or on an airplane that's experiencing turbulence. But actually, after some point, I forget how many seconds it takes, you stop like accelerating. You hit some terminal velocity because the air resistance you feel is canceling out the acceleration of gravity. So you actually end up falling at a constant rate. That's the terminal velocity. And then something very amazing happens. You don't feel like you're falling at all anymore. You just feel like you're floating. I kid you not. You feel like you're floating. I have not done it to like really like say that's true, but it is true. I'll go skydive tomorrow and verify it for you. But it's true. You won't feel a thing. You feel a bunch of air in your face, but you won't feel. You'll feel weightless. It's as if you're in outer space. This kind of makes me want to do it.
You can figure out how long it takes for you to get there.
How long it takes to achieve terminal velocity? It's probably a very easy calculation. You just need to know how to parameterize the drag for the air resistance.
Yeah.
We'd have to make an assumption. We'd have to make the assumption that air resistance is equal to this amount. Like it's a function of velocity. The faster you go, the more air resistance you get. And then you set air resistance equal, you take the derivative of that, and then you set that equal to the acceleration of gravity and see at what time are they equivalent. Solve for the t that makes them equivalent for the two functions. And you'll be able to solve how much time that takes. Maybe a problem like that will come on your next quiz, next Friday. Maybe. Actually, I might. A quiz. I said quiz. Did I say test?
No.
Okay. Calm down, Ivor. No, you just took a quick test. Calm down, bro. Not yet. You get another test soon, but not that soon. Okay. But yeah, it can be done. It's not that bad. The hard part would be how do you create an equation for air resistance? And engineers get paid a lot of money to come up with very accurate equations for air resistance.
Well, it's got some humidity, wind, stuff.
And the shape, right?
Yeah.
Is a cube falling? Is a sphere falling?
Yeah, they fall.
Is a human fall? A human is a weird shape, right? So depending on your shape, oh yeah, you can approximate yourself to a sphere. You can approximate yourself to a square. Eventually, you have to make some type of approximation. And then you can say, okay, what's the air resistance? And then you can calculate it. It's very interesting. But airplanes, there's a lot of money that goes into optimizing less air resistance in airplanes and stuff like that. Okay, so that's that. So we know how to take the derivative of stuff. Now let's work in reverse. Let's say that the acceleration of an electron, actually no, we're tired of electrons. Let's say this is the acceleration function of, I can't say a photon. Photons never change their speed that we know of. So let's say, who has a favorite fundamental particle? Yes.
Well, it's a quark.
A quark? Okay. Let's say up quark. This is the acceleration for an up quark. To us as mathematicians, it doesn't matter what it is. We're just like, let me take the integral of this real quick. So let's say this is its acceleration function. And we aspire to find the position function of the up quark. The up quark is inside a proton and it's accelerating like this. Chances are this equation doesn't truly model the up quark. Highly likely that that's not the true model of an up quark, so much acceleration in it. But for our purposes, we can assume that it's true. That means I need to find first v of t, and then I need to find r of t. That's what I really want. So what are we going to have to do to a of t? Yes. We're going to have to take the integral of a of t, which is equal to the integral of each of its components. Oh, t cubed integral for dt. Okay. So what's the integral of t squared? Yes. guess we can say plus a c, if you'd like. We say plus a c1. Then what's the integral of t cubed? C2. What's the integral of t to the fourth? Yeah, so notice that the same thing as 1/3 t cubed, 1/4 t to the fourth, 1/5 t to the fifth, plus C1, C2, C3. Like vector addition, right? So we can just say, let's just define this quantity as C. This is now called the vector constant of integration. So we can just say that this is equal to V plus C. But we want to define position. So R of t is then the integral of V plus C t. And an integral is a linear operator. So it travels to both the terms integral of V dt plus integral of C dt. Right? So then what we're going to get, this is going to be the integral of V. So we integrate this guy. So the integral of 1/3 t cubed is 1/3 times 1/4 t to the fourth, comma, plus my, let's say, k1. The integral of 1/4 t to the fourth becomes 1/4 times 1/5 t to the fifth, plus some integration constant k2. The integral of 1/5 t to the fifth would then become 1/5 multiplied times 1/6 t to the sixth power, plus some integration constant k3. And so by the same token, this is equivalent to some acceleration plus some constant of integration k. And don't forget constant of integration c. So we can actually define k and c. We can call this, let's call it m, or let's call it n. No, let's call it psi constant. So psi. So this becomes a plus psi, where psi is just defined as C1 plus K1, comma, C2 plus K2, comma, C3 plus K3. You guys see that? Yes, sir.
So where did you get the case from?
Oh, very good question. So remember how we got some C's up in here? Every time we integrated, you created a C. It's like an integration constant. Well, we put the C's into this C vector, and then we had to integrate this whole thing again. Because when we integrated acceleration, we got this. Then to find position, we had to integrate this. So integrating this turns into this. Then when we integrate V, we get this stuff. Oh, and actually, I forgot to truly integrate C. I actually forgot to truly integrate C, right? So we get this here for integral of V, but actually, I need to adjust this here because we didn't truly integrate C. Correct. It would be C1t plus some other constant psi 1, C2t plus some other constant psi 2, and some C3t plus some other constant psi 3. Maybe that's why you were confused. But really, k is an integration constant. K1, K2, K3 is an integration constant. Psi 1, psi 2, psi 3 is an integration constant. Because recall, in general, the integral of like f of x, dx is equal to the antiderivative. It's not a vector, this is the function, plus some integration constant, c.
So, and then that side, that's just standard for, like, that'll be every time you have to integrate twice.
Yes, so here's why actually we even say this in math. This plus c is here for a reason. Because what if we want, when we do this, what if we want to go in reverse? Let's say now that we integrated, what if we want to go in reverse? Let's differentiate. When the differential operator d dx hits this guy, the fundamental theorem of calculus says that the integral just goes away. So all I get is my f of x. When the differential operator hits this guy, it also hits this guy. So when it hits the constant, it just becomes 0. Thus 0. And when it hits this guy, the derivative of the capital F is just lowercase f. So we restore our original equation. So even if c was equal to 0, this works. Even if c was equal to 5 billion, this works. Even if c was equal to negative 27, this works. So that's why we put that c there, because it makes the math more general.
So, what's the variable or the constant that we use if we have to integrate 3 times?
That's a good question. When you get into differential equations, you'll realize that you can solve for these constants given initial conditions. But at this point, all you got to do is just put a C, C1, C2, C3. Just label it some letter and say that this is some constant. All the constants could be equal to 0, but they could also not be. It depends on the situation. Cool thing is, let's say you had this guy, V, right? This is a V of t, it's equal to all this stuff. Notice that what happens when we think about V of 0? Then we're able to solve, this is what I mean by when you take differential equations, you'll be able to solve for those constants. Look at what happens when we take V of 0. This is called an initial condition. Because at time equals 0, this is our initial situation. Notice that everything here becomes 0. All that remains is these constants. And let's say we have like a measuring device that can measure precisely what was the velocity right at t equals 0. Then we know what this hand equals, and we can solve for this hand. Then you can solve for those unknown constants based off of your given situation. That's why this stuff is so powerful. It's amazing, mind-blowingly amazing.
So in our equations, could we re-represent everything in terms of the initial?
Yeah, but you need to be given the initial condition.
Yeah.
I said V of 0 is equal to this, but I need to know what exactly was V of 0. Was it 30 miles per hour? Was it 3.0 times 10 to the 8 meters per second? That's the speed of light.
Yeah, I was going to say that.
That's the speed of light. So a quark can't go the speed of light because it has a little bit of mass. But, we're just saying, what is that initial V? We would have to like measure it in a laboratory somehow.
Well, I would just say like, not like actually put a number there, but just put like the term V naught.
Yeah, in principle, if we can discover what this numerical value is, then we can solve for the constants. Because this V naught should equal some like V1, some V2, some V3, and say that's just like for example, 1, 2, 3. Well, that's equal to this C1, C2, C3. So guess what? We solved it. C1 is 1, C2 is 2, C3 is 3. If, let's say, you're given something like that. In principle, So we integrated, we differentiated. Now there's circular motion. I've seen pictures, but I'd love to see the northern lights in person. That's right. So then we have motions, uniform circular motion. You've seen that in physics. Motions of a projectile. You've seen that in physics. Let's talk about something that okay. So let's talk about, I'm having to pick and choose. Am I going to do Kepler's laws, or am I going to do tangent and normal components of acceleration? I pick tangent and normal components of acceleration because with that we could do Kepler's laws. Because of that dang quiz. The quiz chews up 15 minutes of my time, my 50 minutes. So I only got like 35 minutes to try and get through a section. Man, that's not possible. Especially when I like giving you guys so much extra really cool information. When I was a student and the professors gave me extra cool information, that was my favorite part. My favorite part was the stuff that was just extra, that wouldn't, it's not on the test, but it like satisfies your curiosity. I really like that stuff. So recall, what did T equal? Capital T. It equals R prime of T divided by its own magnitude. Let's say unit vector of your derivative. But note, based off of what we've been talking about today, this is the same thing as a velocity over its magnitude. All right? And then we could say that our capital T is the same thing as this. So our velocity is our unitized vector for unitized derivative vector, but it's scaled by the magnitude of the derivative vector. No, this is a V. V and R are messing me up here. If that was an R, I would have had to put a prime on it. But because it's a V, it's no prime. Okay? So you could take the derivative of both sides here. Right? So then we get acceleration on this end, and you'd get prime over here. Okay? Oh, but actually, one thing we can't forget here is that this is a function of t, and thus this is also a function of t, okay? Even though this will end up giving us a constant, it is a function of t because at various values, it will also have different values. It's not a real constant. It's a constant when you plug in for a real number t. But when you don't, it's actually like a variable equation. It's like the square root of each of the components squared at the various values. So we can't just say that the derivative of t times this guy is as simple as just, oh, ddt ignores this magnitude of v of t. Magnitude of v of t must actually be treated like a function. So we actually have to do the product rule here. Okay. So then we can use the expression for curvature, the kappa for curvature is equal to, what was it equal to? T prime over r prime, magnitude of T prime over magnitude of r prime. Okay, but that's the same thing as magnitude of prime. R prime is just V. Okay. So that means that the magnitude of T prime is equal to KV, into vector arrow. So this is an amazing result because it's saying that the rate of change of our T prime, the rate of change of our T is actually the curvature, and we will be scaling the curvature vector with the magnitude of the velocity. So from the original, from the section before, recall that that n was equal to this. Oh. Okay. So that means if I solve for this guy here and put n there, I get that this is, so I get that this right here is equivalent to divided by n is equal to this guy. So that means I can solve for vector t prime, and that's vector k, vector n, magnitude of vector v. And so this is an equation in your book. So then our equation above, this guy, for acceleration, when we plug in for what t prime is, we get that it equals, plug that into this equation here, we get, and this is the last thing I'll say because we're running out of time. Plug that in here, and we didn't even get through this section because of the quiz. So I'm gonna have to like talk about a little bit more of this section on Monday, and this chalk is running out. So then we end up getting acceleration is equal to v prime t plus your kappa v squared n. So we'll talk about this more on Monday. What I'll do is I'll post what the assignment for this section is, but it won't be due in a week from today. Okay? It won't, because we didn't get fully done with it. But that'll give you the opportunity to read ahead in the section and try to attempt the problems. About the exam, I'm going to grade it and turn it back to you on Monday. I would go over the exam, but in order to preserve class time, I'll just post the solutions to the exam on the Files tab in Canvas, so you can look at that. And if you have any questions, let me know.
On that equation in the yellow, between the k and the n, what is that?
A v squared. Oh, I didn't do this. I gotta get better at that. Putting the hat on the v. I wasn't able to get to anything meaningful in this derivation. Matter of fact, I probably should have elected to do Kepler's laws. There's quite a bit of derivations there, though. You gotta do what you can.